Hello, everyone. Welcome to the vernal equinox presentation at Griffith Observatory. Today, well, will be the first day of spring, although it is the first day of spring, but we're not quite there yet. I'm Dr. David Reitzel, and with me today is Patrick So, as always.
Hello.
And also our observatory director, Dr. Krupp, is with us as usual on our equinoxes. Today, this presentation, as always, is brought to you by Griffith Observatory, the Department of Recreation and Parks, and the City of Los Angeles. And we also, as always, thank Griffith Observatory Foundation for all the support and thank all the members. Today, it's a little bit cloudy here at Griffith Observatory, but we are here to celebrate the first day of spring. And we're going to tell you a little bit about what that means and what today is. It is the vernal equinox. Although it's the first day of fall for folks in the Southern Hemisphere, you'll hear about that little twist as well. And then hopefully if the sun peeks out, you'll get to see local solar noon occur here at Griffith Observatory in the Gottlieb Transit Corridor upon our Meridian arc. And before all of that happens, though, Patrick and I are going to tell you a little bit about what is happening today. And then Dr. Krupp is going to tell you about inhabiting the Meridian and all about instrumentation of that sort. And then, like I said, we'll keep our fingers crossed for the sun to appear and you'll get to watch our Meridian arc in action. So that's what we have in store for you. But first of all, today, as you can see on our slide, vernal equinox, Monday, March 20th at 2:24 p.m. Well, it's not 2:24 yet, so the actual moment of the equinox is in the future. And so, Patrick, what is that about? What does that mean?
So technically, we are still in the last throes of winter, and so that 2:24 is the official time, and that's 2:24 Pacific Daylight Time. That's the official start of the spring equinox, or the equinox, or the first day of spring. And that happens when the sun is located exactly on the intersection of the celestial equator, that's the Earth's equator projected into the sky, and the zero right ascension line or longitude in the sky of those two coordinates. And that happens as the sun moves on its annual path across the sky, which is represented by that line that you see in pink, which is the sun's path across the sky. And it looks like during the year, as the sun moves along that path, but actually we're moving around the sun, so it appears the sun is moving around the sun's path, or what we call the ecliptic. And it happens to today at 2:24 when it arrives exactly on the equator and the zero longitude of right ascension. That exact moment is 2:24, and that's the beginning of spring. So very exciting, and we are not too far away from that. Now, I'm just going to switch to another slide. There we go. So what's happening? Well, the sunlight is hitting the Earth at exactly the north and south pole axis. So so we're getting for all over the world approximately equal amounts of daylight and nighttime. And also at 2:24, that's the beginning of spring in the northern hemisphere. Conversely, it's also the beginning of autumn in the southern hemisphere. So it's quite the opposite. So it's very interesting, and that's what's going on.
Well, very good. I've lost control of guacamole, Patrick, just so you know. So
Okay.
I'm going to log out and log back in and see if that fixes it for me. But just so you know, I might need you to run the slides, but we'll try it here. Yeah, I'm only seeing a black screen on the stream cart slides now.
Okay. Let me see if I can advance a
Yeah,
slide for you. There we go.
that would be great.
There we go.
Okay, I'm also not seeing what slide is up. It looks like it's back on. Okay, well that's the slide. Okay, yes, it's correct now. So if you can go ahead and start this slide for me, Patrick, that would be terrific. Start the animation. It's an animated slide.
Oops.
Well, it was supposed to be. Anyway, well, let's just move on. Move on to the next slide and we'll continue on here live Live broadcast, everybody. You can tell it's live. So, as you can see, today we are going to celebrate local solar noon, which is also known as high noon, as you can see here in this Gary Cooper movie from back in the day. That was a time that in the old westerns, everybody could agree at the moment of time. You'd wait for the sun to get higher and higher in the sky until it reached its highest peak and then started to descend back towards the western horizon. And today we are going to celebrate that moment. If we can get to the next slide. You can see here solar noon is that moment where it's highest and it's in between the sunrise and sunset. Now, this is a different time for everybody on Earth. It depends where you are. And if we can take a look at the next slide, it does not correspond to clock noon, however. If you'll notice, clock noon is already passed for us. We are on what's known as daylight time right now. If we go forward another slide, you can take a look at our time zones here, and those time zones are pretty wide. And not only do you have things like daylight time that shifts the time relative to the sun, but you also, it depends on where you are in that time zone. So if you're in the western part of the time zone, the sun will pass overhead at a different time than if you're in the eastern part in let's say eastern Nevada over there, the sun would be overhead at a different time of day. It would be overhead earlier. Let's take a look at our next slide. Of course, the entire world is divided up into time zones, and those time zones are not straight up and down lines. They are often moved around for political reasons, for economic reasons, for folks. Anyway, all sorts of reasons. They go all over the place. So your time zone can affect what time it is relative to solar time as well. And we can go forward another slide. As we were saying today, we are celebrating what's known as the first day of spring for the northern hemisphere, and in the southern hemisphere, you can see it's labeled as autumn on March 20th. Now, this is all due to the tilt of the Earth's axis. As you can see, as the Earth orbits around the sun, the axis remains pointed in the same direction. It's pointed towards the north celestial pole, where Polaris is very close to that location, and the Earth spins. And because the axis is in the same direction, sometimes and tilted, sometimes the northern hemisphere receives more light, as we do in the summer, or in the winter time we receive less light. You can see that the pole there is completely shaded. And today we are celebrating the northern hemisphere spring or southern hemisphere autumn. And we can go forward another slide. Don't go stare at the sun today. I know you'll be tempted to, but don't go look at it. It's not safe to do unless you have the proper protection like these folks actually have. So safe to do. There are sunspots. I don't think they're any large enough to see with the naked eye just yet, but we are getting into that time of year. We can go forward another slide. This one is interesting because these are real images and these are real data. And you can see on the equinoxes that shadow is more or less straight up and down relative to the pole. Whereas on the first day of summer and on the first day of winter, or for the northern hemisphere, that is, I guess it's for both first day of summer or winter that they switch for northern hemisphere and southern hemisphere. But you can see that shadow is tilted, and that's due to the Earth's tilt. We've removed the Earth's tilt out of these images, and that causes the shadow to look tilted. So we can move forward again. Yet today, a lot of folks think, okay, great, we're headed back into springtime. You can see here that must mean we're getting closer to the sun. Well, actually, that's not the case. The Earth is closest to the sun in January. January 3rd, Earth is closest. So we are slowly moving further and further away from the sun until we are furthest on July 3rd at 152 million kilometers away from the sun. Now, it doesn't vary by a lot, but it is enough that we are closer in the northern hemisphere winter time. So that is not the cause of the seasons. The seasons are actually caused by that tilted Earth's axis. Let me take a look at the next slide. And on this one, again, that first day of spring, like Patrick was talking about, is due to the projected motion of the sun around the Earth. Now, as we all know, Earth revolves around the sun, yet to us, it doesn't feel like we're moving. If you ask an average person, does it feel like we're moving very fast around the sun? No, it doesn't. So it makes sense to sort of create a model where the sun appears to move around us. And today it's at that position that's marked on there with those black dots where the sun is at that location where the equator and that ecliptic cross. And now we can move forward to the next slide. We are going to celebrate this local solar noon down at the Gottlieb Transit Corridor with our Meridian arc that you can see here. And our very own observatory director is here to tell us all about that with a presentation, Inhabiting the Meridian. Dr. Krupp, are you there?
I am, and thank you very much, David, and Patrick as well. Appreciate very much your joining us for a questionable equinox as far as the weather is concerned. And the fact is, I want to thank everybody for tuning in today to Griffith Observatory Television and for observing with us the vernal equinox, and in particular, as you said, a short time from now in having a local noon at the Gottlieb Transit in the Northern Hemisphere. I have to ask for a little bit of technical help here because we're not switched over to the slides that are needed for this presentation. But I will indicate at least that as a prelude to local noon, we'll spend a little time with the Meridian. And also note that it's inextricably linked with local noon. But let me just pause a second here because I'm having trouble getting the imagery that we need for this presentation. Let me just. I hear the footsteps of our technical staff, I think.
I think so too. This is probably the same issue that I was having, and here they are to solve it for us. Luckily, the universe waits for us when these sorts of problems have. The local solar noon will just pause until we're ready. Now, all jokes aside, it will happen like clockwork, but we are professionals here and we'll have everything sorted out.
There it goes.
So we got to go back a bit.
We thought you were clicking on
it. Okay. Obviously, thanks to our technical staff for saving us all and proceeding as well. You know, it's this kind of poetic response in live broadcasting that is befitting of the day. The sun is toying with us in Los Angeles today. And it's tricky to know whether or not we're even going to have some sunlight, but we're game to play, and so we're moving forward. But in any case, local noon, as you've heard, occurs today at 1:01 p.m. Pacific Daylight Time. That'll happen whether the sun's visible or not. And as you've also heard, the exact moment of vernal equinox will occur just an hour and 23 minutes or so later. 2:24 p.m. Well, the meridian, of course, is a fundamental reference in our system of directions. And it's really just the line that runs on the ground from true north to true south. And wherever you go, there you are on some local meridian. And in fact, the many monumental antiquities were intentionally aligned with it. The maps that we use are in fact oriented by the meridian. There's a map of Washington, D.C. laid out on a square, but in fact, even though it's the corners that point to the cardinal directions of D.C., that is still cardinal orientation on a meridian line, and in streets and boulevards as north, south, and east, west. And in fact, Griffith Observatory, the design of Griffith Observatory adheres to the same kind of plan. Well, the meridian originates in the basic behavior of the sky, and it is a fundamental astronomical reference. It's probably most familiar to people as the prime meridian. That's the meridian at Greenwich, England. Greenwich Meridian serves as the adopted 0 point for longitude on Earth. It is a primary attraction at the old Royal Observatory at Greenwich. People go there, they stand on the meridian, and people sit on the meridian, and of course, people observe on the meridian. So the meridian is a north-south line. It's that line on the ground in the diagram, and we're looking north in that picture. And we identify those directions, north and south, through the most fundamental motion of the sky. It's daily rotation. Thanks to the spin of the Earth on its axis, the entire sky seems to turn around a single unmoving point in the sky, and that point is the North Celestial Pole. And Polaris the North Star, the pole star, is just fortuitously close to that particular position. And we can detect that motion in a photograph like this just by leaving the camera open for a time exposure. And the trails of the stars in that vicinity leave portions of circles around them as they move. This looks like, oh, maybe a 50-minute exposure or so. And as a consequence, it sort of looks as though they're circles all over the place. Well, the direction on the ground directly below the North Celestial Pole, again, is north. And that, in fact, is how the direction north originates. We wouldn't even be talking about north if the world did not turn. But of course, as the world turns, then the sky delivers directions. And as the sky rotates around the North Celestial Pole, or seems to, the objects in the sky, the sun, the moon, the planets, and the stars, all cross or transit the meridian. In this celestial sphere drawing, which imagines the Earth in the center of a spherical universe, a sky on which all of the celestial objects are located, this happens to be the configuration for the sun's path in the daytime on the winter solstice in Los Angeles, which in fact is at the top of the globe, as it properly ought to be, I suppose, in the picture. And the sun rises in the southeast, crosses due south, and sets in the southwest. In that point where the sun is highest on the meridian, that arc that goes from the south point in the foreground to the north point in the background, that in fact is the transit of the sun. And at transit, any celestial object is at the summit or top of its arc across the sky. Well, the word meridian is rooted in words that mean midday or noon. And when the sun transits the meridian, it is local noon. When the sun is east of the meridian, it is ante-meridium or AM, which means just before midday. And when the sun is west of the meridian, it is post-meridium or PM, that is after midday. That's where those terms originate. And for the record, noon is neither AM nor PM, and the same is true for midnight. They're just 12 noon and 12 midnight. They're in between and not part of either territory. So the meridian is then a time and a place and a direction. And the meridian is also that celestial arc that vaults the sky from the north point on the horizon through the zenith directly overhead to the south point on the horizon. And every month, astronomy magazines like Sky and Telescope publish an all-sky map equipped with the celestial meridian and the blue vertical line that bisects those charts from north to south with the zenith at the chart center. And we have, in fact, from the surface of the Earth, very clear distinction between north and south. It is, in fact, profound. The stars travel in circles, or at least appear to, around the north celestial pole, as the diagram indicates. But if you turn around in completely the opposite direction and looking south, well, then, of course, what you see is the fact that I think we're stuck again. Stuck on the slides. Let me ask if anyone can advance.
I am here, and I am also once again just seeing a black screen. So
yeah,
it is advancing when you hit it, but that doesn't help you, of course.
Oh, thank you. I can actually see it here. So I've been jumping ahead, even though I can't see it here. Okay, I got you. Thank you. Well, when you're looking due south, the stars appear to follow these longer and flatter trajectories. They are still traveling in circles, but their migration does look strikingly different because of the tilt of the sky compared to our position on the Earth. Well, our ancestors were aware of these directional distinctions, and of course, of our ongoing use of them is really just a perpetuation of old habits. Evidence of these habits shows up in many ancient and prehistoric sites. So, for example, a natural rock shelter in Ventura County at Alder Creek, this is in Southern California, a site that is enriched with Chumash pictographs, seems to have been chosen for this symbolic enhancement because just by chance it opens due north. And there you are inside the shelter and looking out and you are, in fact, looking toward true north. The geology and the geography have just conspired to make that so. The slope of the ceiling permits a view of the northern sky and the north celestial pole. And so at night, when you do another one of those time exposures, you can see that the view of the window out the shelter is, in fact, more or less centered on Polaris. Interestingly, there's a natural crack in the rock, the ceiling, the rock that forms it, and that crack, rather obvious, is on axis to the upward slant of the north pole of the sky. Again, a completely natural phenomenon, but apparently something that was of interest to those who made the shelter filled with pictographs, because all those creatures that are painted there are all headed in that same direction, up toward the top of the sky, toward the north pole of the sky, which was a destination of supernatural and shamanic power in Chumash tradition. This same principle is deliberately expressed in monumental architecture in Chaco Canyon in northwest New Mexico. Pueblo Bonito, which is visible here, is a large multi-story apartment complex, and it's oriented with the meridian, and it commemorates its orientation in a north-south wall that bisects the two principal zones of the building's plaza. In the plan of Pueblo Bonito, in this ancestral Pueblo monument in New Mexico, you can see that at the bottom is that east-west line, which is in fact entirely accurate with the level that you would expect from making such a survey with the unaided eye. But that cardinal orientation serves a greater purpose in Pueblo Bonito. There's a north-south wall. You can see a segment of it right in the middle of this view with two underground ceremonial chambers, or kivas, great kivas on either side. And so that wall split Pueblo Bonito into two halves according to the meridian. Beijing, in the People's Republic of China, is the only world capital that still adheres to a sacred cosmological plan. During the Ming Dynasty, it was laid out on the meridian with a north-south line that has actually been preserved by the current government. And this diagram of the imperial palace, the heart really of historic Beijing, shows that it's aligned with the cardinal directions and, in fact, on axis with that meridian. It's apparent in the ritual walkway of the imperial palace. This time it was focused on the emperor, who held court in the Hall of Supreme Harmony, which is in the center of this view, and the walkway leading directly there. This line was focused on the emperor, and he was the sky's agent on Earth and the terrestrial counterpart of the North Celestial Pole. Just as all the stars circumambulate around the North Pole of the sky, which is in Chinese tradition the visible face of the high god Shangdi, the court circulated around the emperor here on Earth and in the imperial palace. Egypt's Great Pyramid at Giza and the rest of Egypt's pyramids are cardinally oriented as well. And by incorporating cosmic order into monumental architecture, the Egyptians miniaturized the cosmos in this terrestrial setting and thereby transformed it into sacred space. The three pyramids at Giza are all obviously aligned to the cardinal directions in the plan there, but so is the entire cemetery area that's on all sides of the main pyramids at Giza. They all, in fact, obey that principle. These principles also can be seen at the observatory of Guosho Jing, 13th century Chinese astronomer. The observatory is at a town called Gaocheng in north central China, and it operates like a sundial to establish and refine the calendar with shadows that are cast. The sun at different heights, very high in summer, much lower in winter, will cast shadows of different lengths through a doorway up top. And by casting the shadow of a horizontal bar, that bar's shadow will fall then on the extended wall. We're looking down at it to the north, and the shadow fallen on that wall will permit very accurate observations of the date of the year. These principles were applied even more elaborately in the 14th century by the Islamic astronomer and ruler Ulugh Beg at Samarkand in what is now Uzbekistan in Central Asia. His observatory is in ruins today, but the huge meridian arc that once existed is in evidence in this section of his observatory. And in fact, he put that arc on his meridian. There's some element of the underground portion that still does survive in Samarkand today. But that arc was used then to observe transits of the sun and other objects. The sunlight is beaming onto that arc, which is inscribed numerically so that you can make measurements on behalf of timekeeping, calendrics, and in fact, star mapping. Well, Europe developed its own calendrical revelations in architecture with giant meridian scales that were installed in arches. And at first they were intended to monitor the progress of the year calendrically, but these meridianas were eventually inscribed on church floors by astronomers for precise measurement of the sun's daily noon elevation. There is one of these shown in elevation here with a high wall on the left side, and there is a hole up near the top which permits the sunlight to shine through and then hit a line that's inscribed on the floor. And of course, once again, the length of the shadow is related to the height of the sun. So the aperture on that vertical wall rising beyond the south end of the calibrated meridian line permits a pinhole image of the sun to cross the meridian each day at local noon. And the point where the sunlight intercepts that line depends, of course, on the sun's noon elevation. Because that angle depends on the date, a meridiana operates as a calendar. And this elevation illustrates a meridiana that was designed by Ignazio Dante in San Petronio, which is a 14th century Gothic basilica in Bologna, Italy. He did that in 1575. Now, Dante's San Petronio Meridiana was never completed. It was replaced in 1655 with an even grander Meridiana designed by the astronomer Giandomenico Cassini. You see a portion of that looking, in fact, to the south inside the cathedral. So here, in fact, is the other direction for this 220-foot long element in the church. And here is the sunlight crossing the meridian at local noon on November 18th in 2004. And of course, the Meridianas can be found in other places as well. Italy, for example, has yet another one in the upper part of Old Bergamo. This is in northern Italy, and it's operating like clockwork on October 14th, 2009, where the spot of sunlight is crossing the inscribed line. So, of course, formal observations of the sun's meridian transits persisted in national observatories, like the Paris Observatory, the cornerstone of which was laid on the summer solstice in 1667 during the reign of Louis XIV. France adopted the axis of the Paris Observatory as its preferred primary meridian. Jean-Dominique Cassini was invited to Paris to assist the development of the new Paris Observatory, and he became the first director. Extending the inquiry he had undertaken at San Petronio, he constructed a large meridiana in the Great Hall of the second floor of the Paris Observatory. It's there in the image, and it's 96 feet, 10 inches long. He wanted the building to perform as an instrument, and he designed his meridiana to coincide with the meridian of France, which in fact continues on the lawns and the pavements outside the observatory. With it, he planned to obtain a more precise determination of the apparent annual motion of the sun. Despite the French predilection for a French prime meridian, the local Greenwich meridian occupied by George Airy's transit circle was officially adopted as the prime meridian of the world in October 1884 at the International Meridian Conference held in Washington, D.C. Airy was England's astronomer royal, and his transit circle at Greenwich Observatory was used in the service of British cartography. The old Royal Observatory had been established in 1675 by King Charles II, who wanted it dedicated to, quote, finding out the longitude of places for perfecting navigation and astronomy. Well, long before England and France drew a line in the sand for the 0 degrees longitude, astronomy in medieval India staked a prime meridian through Ujjain, which is about 400 miles south of New Delhi. Ujjain is in central India, and there's the plan. It was believed to occupy the Tropic of Cancer, and that in part accounts for its status. Sawai Singh II, the Rajput ruler of Jaipur, built Ujjain in 1730 and 4 more monumental observatories. And his most elaborate observatory is at Jaipur. There, the great Samrat Yantra makes sculpture and architecture out of an instrument. It includes a particularly interesting component. That's the Sashamsha Yantra, which is a cardinally oriented room that houses a pair of inscribed quadrants. You see one of them there, and permits light from the transiting sun at local noon to enter the darkened chamber through a pair of small holes that penetrate the southern wall. When you're looking up, you see those 2 holes as in this view, and a little bit of the sunlight is already falling against the nearby wall. These holes project pinhole images of the sun on 2 quadrants and permit direct observation of its astronomical declination, which is linked to the calendar and the progress of the year. See the second one there. Well, there are all kinds of meridians around the world, but anyone who collects meridian markers now has to navigate a course to Los Angeles. Everybody knows about the Greenwich Meridian, but this is the Griffith Meridian. Griffith Observatory is cardinally oriented. It faces north, and we're looking south here, and its telescopes are aligned with the North Celestial Pole to facilitate continuous tracking of celestial objects. There's the Zeiss 12-inch, and in fact, it happens to be pointed at that time right toward the North Pole of the sky. And there's a comet in view as well. There are all kinds of meridians around the world, of course, but this one is in fact particularly sweet because the observatory was conceived and constructed to conform to the needs of modern public astronomy. Its Greek revival, Beaux-Arts modern architecture, reflects the traditional vision of cosmic order. Telescopes operate on this principle. The telescope is rotated around the polar axis at a rate that compensates for the turning Earth. And the sundial is also aligned with the meridian, and that permits its shadows to convey time systematically. And the mirrors of Griffith Observatory's triple beam celestat or solar telescope are also on the meridian. The Griffith Meridian is actually part of a singular and monumental public instrument, the Gottlieb Transit Corridor. There's really nothing like it anywhere else in the world. This instrument is integrated into the observatory's new architecture on the west side, where parallel glass walls, 150 feet long and 20 feet high, preserve below grade the observatory's signature vista of the western horizon. This instrument demonstrates how the sky works through meridian transits of the sun, moon, and stars over the walled corridor. The corridor, 10 feet wide, is bisected by the bronze meridian line set into the concrete floor, and it extends the full length of the walls which frame the celestial meridian and turn an astronomical abstraction into a visual experience. The architecture then reveals astronomy. At the north end, the meridian line climbs a stairway constructed to ascend at the angle of the North Celestial Pole. And so at night, visitors can sight the North Star along the stairway's central banister. The fundamental character of Griffith Observatory is indicated, of course, right on the front of the building, where it says Griffith Observatory. And that's what Griffith Observatory is. It's an observatory, and it puts visitors eyeball to the universe. Griffith Observatory, as a public observatory, has a building filled with instruments, and all of them deliver real data and real experiences and transform visitors into observers of nature and the sky through instruments. So we are, in fact, at Griffith Observatory, mobilized by the concept of the building as instrument. The Gottlieb Transit Corridor is just another dimension of that immersive encounter with the sky. And there is more to it than the long glass corridor, the north-south, the North Stairway, and the bronze Meridian line. At the south end, a tall and night black monolith supports a stainless steel foil. And on the ground, just north of the monolith, stands a massive and inscribed bronze and stainless steel Meridian arc. And above it, on the inside face of the glass wall on the west, is mounted a huge and heavy ecliptic chart, which can be seen just to the left and above the Meridian arc there. Well, the foil attached to the monolith is equipped with that complicated and technically advanced device, a hole. And as an object, say the sun, transits the corridor, its light passes through the hole. Where that light falls depends on the angle the object makes with the horizon. And an object, again, reaches its highest elevation when it transits. Well, the monolith and the foil permit light from the transiting sun to strike the meridian arc, where the sun's image, about 3 inches in diameter, announces the date on a scale inscribed with the months, the days, and the corresponding ecliptic chart constellation figures. Special emblems spotlight the solstices, the equinoxes, and the major standstills of the moon. Well, people walk inside the transit corridor and they watch all of this. They also watch it from the terrace above. Actually, Tycho Brahe already did something like this. In 1582, he fabricated and installed a large bronze engraved meridian arc for transit observations at Uraniborg, the castle observatory he built on the island of Ven off Denmark. We, however, have linked the meridian arc, where the sun makes its daily noon transit, with that big star chart up on the wall. And as the sun's light reaches the center line of the meridian arc, it activates sensors that are running the length of the arc. They then transmit a signal to the giant ecliptic chart, and that signal prompts the illumination of lights that mark the current position of the sun along the ecliptic and the stars that are with the sun at that time. Now, those stars are invisible, of course, because it's daytime, but the device in real time allows you to see the sun's progress through the year among the background stars. So the meridian is, in fact, a place and a time and a direction. And when visitors arrive at this junction of Earth and sky, they occupy a place where space begins, a cosmic modem that downloads the sky. They connect what happens in the sky with place, time, and direction here on Earth in a dramatic and precise and content-rich revelation in light. The meridian is not then just an instrument or a concept. It is a stage, and the universe performs on it daily. It is unclear whether the universe is going to perform daily on that Meridian arc today, but I am about to head out to the transit corridor, take a look and see exactly what our chances will be and what our options are if, in fact, the sun decides to hide its face after all. So thanks very much. I'm abandoning you here from my office and headed out to the transit corridor just off the lower west terrace of Griffith Observatory.
Well, hi, folks. I'll stay here with you to keep you mildly entertained, I hope, while Dr. Krupp makes his way down to the Gottlieb Transit Corridor and to our Meridian arc. It is fascinating that Griffith Observatory really is an instrument itself. The building itself being aligned with those cardinal directions to start allows us to use the building as an instrument. When we're setting up our telescopes, we need to align them to the North Pole in order to compensate for the Earth's rotation. Otherwise, we'd be changing the direction of the telescope all the time, which I've done before while showing off to people, and it's not a lot of fun. Instead, you can install a motor that compensates for the Earth's rotation. But that telescope needs to be pointed towards the North Pole, or at least needs to know how it is oriented. So some of our scopes actually move in 2 axes rather than just one. But an old-time equatorial mount, you actually point the spinning axis, the axis that spins towards the North Pole. So you need to know where north is. And those telescopes we have that are like that, we use the building as an indicator to get us initially lined up, which is interesting. Of course, the Gottlieb Transit Corridor itself that Dr. Krupp is headed down to It is an instrument. Not only does the corridor highlight the celestial, um, the celestial happenings above you in the sky above, and that meridian that projects upwards into the sky, that banister is pointed towards the North Star. So if you're ever here at Griffith Observatory at night, make sure you come take a look and sight along the banister if it's clear enough and you can see the North Star. Which, by the way, the North Star is not the brightest star in the sky. It is a fairly bright star, but it is not one of the brightest, and don't get confused that way. Now, as we wait for Dr. Krupp to get down to the Gottlieb Transit Corridor, do want to point out a couple events that are coming up. On April 7th, we have a very special lecture from Dr. Richard Ellis talking to us about the latest brand new results from JWST and that beautiful infrared telescope that's out in space and the amazing discoveries that are already happening. Dr. Ellis is a real expert in galaxies and in the history of the universe. So April 7th is coming up on that one. And then, of course, All Space Considered, which we just had one last week on Thursday. We've moved to the third Thursday. Our next one is coming up on April 20th. So we think you'll enjoy that as well. So folks, go ahead and sign up to follow us here on YouTube and receive notifications, and you won't miss any of our sky events or any of the lectures that we're doing and that we're bringing to you. So I have a feeling Dr. Krupp is probably getting close to being down in the Gottlieb Transit Corridor now. Our team will let me know when that finally happens. I'm taking a peek, and out my window, I'm not seeing any sign of the sun. It's a little brighter than it was earlier, but I'm seeing clouds everywhere. So maybe they're working out a way to bring you something down there. I'm not sure what's going to happen. We'll have to see. So we continue to wait. Now, of course, Griffith Observatory is brought to you by the Department of Recreation and Parks in the city of Los Angeles. And as always, we like to thank Griffith Observatory Foundation. Griffith Observatory Foundation is our nonprofit partner, and they make so much of what we do possible. Our school programs that serve Our online program is serving hundreds of thousands of students each year now, and our in-person program is slated to return later this year in a pilot program. So if you're a fifth grade teacher out there, make sure you've signed up to our newsletter to receive indications and notifications that that's coming up. But it is our foundation, our nonprofit partner, that makes those programs possible. So thank you to all of our members and to everybody that's made a donation. We very much appreciate that. And we look forward to continuing to do work with all our wonderful foundation. Well, I got report that down at the Gottlieb Transit Corridor, Dr. Krupp is ready. So let's see how the conditions are down there right now. I am seeing the
I
arc.
have, in fact, migrated from my office at Griffith Observatory to the Gottlieb Transit Corridor. And the Gottlieb Transit Corridor has a name with three parts: Gottlieb, Transit, and Corridor. Well, Gottlieb is pretty easy. That's Robert J. and Suzanne Gottlieb, who made a very generous donation to Friends of the Observatory, now Griffith Observatory Foundation, as part of the $93 million renovation and expansion of Griffith Observatory that was completed in 2006. So that part's pretty easy to understand. Corridor, that's not hard either. In fact, I'm in a corridor right now, and as you look down in this direction, it actually looks like a corridor too. So at least I'm not misleading anyone on that score. Transit is the third element. And in astronomy, transit can mean several different things. But for our concerns today, transit, as you've already heard, is all about the passage of a celestial object over the north-south line or meridian. Everybody has his or her own meridian. There's meridians all over the place. I'm standing on one now, but it's not the one that is the Griffith Meridian with the meridian arc marking it. But that transit of the sun, in this case, again, is the point when the sun is highest in the sky, and that, of course, is at local noon. Now, you would think that when we're calling out local noon like that, we would be well coordinated with all of the things that help keep us on track with time. But in fact, today, local noon is going to occur at 1:01. Now, this kind of makes absolutely no sense whatsoever until you think about what's going on in keeping time. It's on the clock, of course, that we talk about 1:01 or any other time. But in fact, the sun in the sky doesn't really adhere to clock time. Clock time is an adaptation that is designed to make timekeeping a little more uniform and a little more convenient for all of the enterprises that we undertake on the planet. So there are three main things that affect and make this difference. First, of course, is exactly where we happen to be. But I should take a step back because this is, in fact, a kind of an odd time as far as even our old clock systems are concerned. We're on daylight time now, a relatively modern invention as far as the history of human beings on Earth is concerned. But that means we've already thrown the clock off of the time that we would normally expect the sun to be crossing our local meridian closer to 12 by moving ahead 1 hour, which we just did about a week ago. But second, we keep clock time according to time zones. And time zones are very wide geographical areas. We're in the Pacific time zone here at Griffith Observatory, but any particular place in that time zone over that span of hundreds of miles will have the sun crossing that local meridian at a different time, but they're all keeping a clock with the same general time. So that's another difference between local noon as it happens in the sun's time and then, of course, on our clock time. But finally, there's one more major factor. And that final major factor is the fact that we are not traveling on a circular orbit around the sun that makes all of these celestial activities seem to follow a very uniform rate. In fact, the Earth's orbit is an ellipse. It's a kind of a squash circle, and that squash circle means that there are times when we're moving a little bit faster and times when we're moving a little bit slower. And that also alters the time that the sun is making on the meridian and what our clocks seem to say. And so we've got, in fact, the astronomers call that difference the equation of time, and most people sort of know about it from the globes that they saw as kids, where there's that funny little stretched out figure 8 that nobody knows what in the world it is, but that in fact is the analemma. And astronomers don't really much care about the analemma, but they do care about the equation of time, and those are essentially the same things, a reflection of the fact that the Earth doesn't travel in a uniform rate in its orbit. So that accounts for the fact that we have local noon occurring at a kind of an odd time, not at straight up 12 on the clock as one might think it ought to occur. But then the next thing that is involved here is how do we actually get a chance to see it? Well, here we are on the Griffith Meridian, and you recall that the meridian is a north-south line. That direction is south, that direction is north, and the line is in fact inscribed right on the ground. And as we've mentioned before, I know that everybody knows about the Greenwich Meridian, but this is the Griffith Meridian, a far classier meridian, of course. Well, the meridian arc is the instrument that is placed on the meridian, and you can see that the meridian line just continues on up to the top there. And if you look carefully at the meridian arc, you can see that it is inscribed. There are dates, months, and then beginning and the end of a month, and numbers as lines for the individual dates in the month. In addition to that, we also have the constellations of the zodiac, the constellations through which the sun passes over the course of a year. Now, you can't really see those constellations with the sun at the same time because the sun is up and the stars then are all doused by the sunlight. But nonetheless, we know because the Earth travels in its orbit around the sun that the sun appears to go through those constellations. Finally, we also all know that the angle at which the sun strikes the Earth changes with the course of the seasons. And that's where the meridian arc and the transit corridor really get down to action. To the south is that big black monolith with the stainless steel foil overhead with the uncanny and very complicated element built into it, high at the top, the hole. So the sun shines through the hole, sends a spotlight of light down on the ground, and as the Earth rotates, it appears as though that spot of light will in fact move more and more to the meridian line as it gets close to local noon. That spot appeared just a moment ago, and now it has eluded us again, and that's what's going on with our clouds today. But we are hopeful we are going to pull this out, a moment of high drama, a cliffhanger at Griffith Observatory. So now when you look at the meridian arc, you see, okay, I've got the elements of this strait, I've got this, this meridian arc, and I've got the dates and the constellations and all, and you say, well, that's really pretty impressive. What you've done here at Griffith Observatory is installed some Stone Age astronomy with some Bronze Age materials and some sort of Renaissance embellishment, and you think, is that all there is? Wait, there's more. Because in fact, this is designed so that as that hole projects a spot of sunlight on the ground and it gradually moves to the meridian arc, you'll see a spot of light here, and then that light appears to move and then cross the actual meridian. And built into the meridian line are sensors, and those sensors activate the ecliptic chart that's up above there. The ecliptic chart is a map of the stars, and the sinusoidal or undulating line that goes through them is the path that the sun follows over the course of the year. And so it moves through all of those constellations of the zodiac, through the equinoxes and the solstices, and in fact the vernal equinox, at the time of vernal equinox, the sun is in Pisces, the fishes, which is up there sort of near the center of the chart. And when that light reaches it, it then activates the ecliptic chart, which lights up the stars of the constellation that the sun is occupying, and also the position of the sun on the ecliptic or its path through the course of the year, in a way that of course you'd never be able to see. Otherwise, you'd have to turn all the lights off on the sky to see those stars. But the Gottlieb Transit Corridor makes them both appear if, in fact, the sky is cooperating. Well, let's see. We're getting closer to 101, but we've got about 8 more minutes to go. And that means that the rest of the architecture of the place has to be appreciated as well. You sense that I have not misled you with the notion that there is a corridor here. But in fact, there's actually a celestial meridian here, because the corridor with these 2 walls creates overhead a ribbon of sky that actually simulates what the meridian really is as an abstraction in the sky. It is a line that goes all the way across from south through the zenith, through the north celestial pole, and out to the north direction. And as mentioned earlier, you don't have to rely on my saying so for that north celestial pole and Polaris, because if you come here at night and look up at the banister, that stairway is in fact deliberately aligned to be the right angle, to be facing up to the north celestial pole and the star Polaris. And so you'll see it lined perfectly with Polaris in place. The entire configuration then is an instrument that's actually built into the architecture of Griffith Observatory, and there is in fact nothing like it on the planet. The meridianas that you find in some of the churches that still have them in Europe are of course operating, but they don't light up the ecliptic stars as they do at Griffith Observatory. Our normal kind of high drama in the ecliptic activities of the transit corridor would involve seeing this spot of light appearing and then moving closer and closer to the sensors. But of course the sun is not cooperating, although as I look at it I see little patches of blue. But where it would appear is right here, circle about 3 inches across, and here in fact is the mark for the equinox. And so when the sun gets to this point on the equinox, that's the key marker, whereas down here, when the sun is very high, it projects an image that falls very low on the arc, at the summer solstice. And as you all know, in winter, the sun is very low when it moves across the sky, and it strikes that other marker that is up near the top at winter solstice. At winter solstice and summer solstice, then you've got the two ends of the meridian arc, but this presents a kind of an interesting problem. If you think about it for a second, the sun, let's say starting at winter up there, is gradually, each day the spot is migrating through the months from December all the way down through March, April, May to June. And then at June, it has to march all the way back up again to December. So how does the meridian arc know when the sun is going down and when the sun is going back up? This seems like a mystery, doesn't it? Well, in fact, the meridian arc can't know which way it is, and that's why we have the switch. This is the solstice switch, and at the solstice, we find the visitor who has traveled the farthest to reach Griffith Observatory on that day, and we have that person throw the switch so that the meridian arc works properly for the next and rest of the year. And then the next solstice, we have to do it all over again. Well, now let's see. We are closer to 12:56, and it seems futile to me in this broadcast to expect that in another 5 minutes the sun is going to come out. And so as a consequence, I'm going to perform an astronomical miracle looking for, Benjamin, come forward. And we are going to produce sunlight no matter what. We've got sunlight. So sunlight is falling close to the equinox line, but that's not going to be good enough to produce the effect that we need. And so we have to mask the oops, here comes, we have to mask the arc. There we go. And moving closer. High drama, please. No, way too fast. Way too fast. Yeah, you got it. Yeah. Make us wanted. So you move closer and closer and closer. And, what the heck. Just go ahead and do it. And are we there? Do we get Pisces light? Okay, so Pisces, the fishes is lined up. The position of the sun is lined up. And this just goes to show that Griffith Observatory delivers an equinox whether there's sunlight or not. So on behalf of Griffith Observatory Foundation, the City of Los Angeles, Department of Recreation and Parks, let me thank all of you for witnessing this. And come on back, maybe even tomorrow, it'll be sunny. No, I don't think so. You might want to wait a week or so. Thank you very much, everybody.
Well, thank you for that, Dr. Krupp. Indeed, I don't think it's going to be clear tomorrow. In fact, the weather is supposed to be worse tomorrow up here at Griffith Observatory. But here at Griffith Observatory, we make things happen for you. We have the ability to, of course, fake local solar noon with a flashlight if we have to. But indeed, local solar noon did happen. Well, actually, it's going to happen in about 2 minutes, but there's no sunlight to have that happen. And again, in a little over an hour, that moment of the vernal equinox will happen where the sun is on the celestial equator, and that sunlight will be hitting Earth perpendicularly. So we can all look forward to a little bit warmer weather, a little bit longer days. Today, we should be getting equal amounts of sunlight and night. Now, of course, you get a little bit more light. The Earth's atmosphere bends the sun and bends the light a little bit, so you're able to see beyond the horizon just a little bit. So we're getting a little bit more light now. So let's look forward to those warmer days. Let's look forward to the springtime weather that's coming. And we'll do another broadcast much like this one on the first day of summer. So look forward to that. It should be around June 20th, June 21st. It varies a little bit due to that equation of time again. So stay tuned. Now, we are not going to go forward with our sunset broadcast tonight. If you're someone that's used to tuning in twice a day on these seasonal moments, well, we are canceling the sunset activity tonight due to the due to the clouds and the increasingly bad weather. But again, make sure you tune in on April 7th for our next broadcast, which is a live lecture with Dr. Richard Ellis talking about the latest results from JWST. And then on April 20th, All Space Considered will return with myself and Patrick and our entire team, Katie Flynn and others, where we are going to talk about the Earth and Earth Month. So we're going to bring you look at Earth as a planet. So we'll do that on April 20th for All Space Considered. Well, thank you for joining us today for our local Solar Noon broadcast on the vernal equinox. Once again, this is brought to you by Griffith Observatory, the Department of Recreation and Parks, the City of Los Angeles, and Griffith Observatory Foundation, our nonprofit partner. So thank you, everyone. We very much appreciate your support, and thank you to everybody that joined in today. And everybody in the chat, it's been a lot of fun on the YouTube chat, and make sure you sign up and sign up for notifications and sign up to get those announcements for all the shows so you don't miss them. And we'll see you on the next event. Thank you, everybody. Have a terrific day.